Towards the end of Module 1, I mentioned the 18th century French geologist Georges Cuvier, who wrote, "Genius and science have burst the limits of space. Would it not also be glorious for man to burst the limits of time?" Well, he'd be quite impressed to know that the tools and methods of science reveal an Earth that is around 4.5 billion years old, and we inhabit a universe that is nearly 3 times that age, on the order of 13.8 billion years old. In this second module, we peer into the very furthest reaches of deep time, and we take an admittedly cursory look at some key origins, like matter, space-time, stars, planets, and our planet, its first continents, oceans, and atmosphere. Thousands of years ago, the philosopher Aristotle taught that the universe had no beginning and no end. And at the dawn of geology, a little over a couple hundred years ago, you may recall that James Hutton wrote, "We see no vestige of a beginning, no prospect of an end." But today, and largely based on the 20th century recognition of galaxies all rushing away from each other, we envision the universe as having had a distinct origin, the Big Bang. And that term was initially a derogatory appellation coined by those who favored a universe with no beginning nor end. Today's understanding of the Big Bang is not an explosion in the stick of dynamite sense, certainly a cataclysmic burst of energy, but literally the creation of all matter and of all space and of even time itself. I'm not a cosmologist, and we have no need for the details of this event in the midst of what is primarily a geology course. But the Big Bang is a prime example of science telling us a whole lot about something that we cannot experience firsthand, and that nobody was around to see. The Big Bang passes the science bar with flying colors because it's predictive and testable. This graph here shows, just in one impressive way, the stretched out and denuded leftover energy of the Big Bang, if you will, the smoking gun, has an expected calculatable character of energy intensity at all different frequencies. In the late 1980s, the Cosmic Background Explorer satellite mapped the sky using the lingering glow from the Big Bang, and it found an exceptional correlation between prediction and measurement. The Big Bang is a very well substantiated theory. Okay, so what do we know about it? It really appears that the universe did have a beginning, contrary to folks like Aristotle and even our beloved founder of geology, James Hutton. And based off careful measurements of galactic recession velocities and the pattern of this first light measured by the Kobe satellite, the Big Bang occurred around 13.7 or 13.8 billion years ago. The why part, why it happened, is much tougher and not well understood. All matter and space-time emerge from an infinitesimally small point. Okay, if you find that hard to comprehend, trust me, you're not alone. In terms of matter generation, the Big Bang created the elements hydrogen and helium, still the primary material stuff of the universe. In terms of matter generation, the Big Bang created the elements hydrogen and helium, still the primary material stuff of the universe. And sure, there may be significant amounts of undetectable matter, so-called dark matter, but we'll leave that to the cosmologists for now. We need to move on to making some stars and planets. And mathematical modeling suggests that a few hundred million years ago after the Big Bang, the first stars began to form. Stars form out of clouds of gas and dust, effectively stellar nurseries like this iconic Hubble Space Telescope image. Protostars are forming from gravitational collapse within sections of the cloud, mostly masked behind the cloak of gas and dust. But as they turn on, generating light and heat, the cloud gets this beautiful hazy illumination. Well, stars are primarily hydrogen and helium, and the very first stars were nothing but. With time, the other 90 or so naturally occurring elements were literally forged in stellar interiors, where temperatures are measured in tens of millions of degrees and pressures at billions of atmospheres, places where atomic nuclei are squished and mashed together to form heavier elements. On the right, the plot of cosmic abundances, effectively how much of each element we find in the universe at large. You might note that the heavier elements with higher atomic numbers are less common, and there's also a kind of an up and down pattern, partly linked to a propensity for even pairs of nuclear particles to be a bit more stable. For the most part, normal stars, including our own, can create in their thermonuclear furnaces elements up to atomic number 26, iron, with, 26 protons. Elements heavier than iron are produced under the exceptional pressures and temperatures produced in cataclysmic stellar collapses called supernovae events. But to be fully accurate, there are circumstances where red giants and neutron stars can and have made heavy elements via so-called slow and rapid neutron capture. Okay, what about planets? Planets are simply leftover star stuff. On the left, a famous image of the star Beta Pictoris. It's in a constellation that you'd need to be in the southern hemisphere to see, and it's quite close, only about 60 light years from Earth. The picture was taken by blotting out the central star and color enhancing the so-called protoplanetary disk of gas and dust out of which the star is formed. In this disk, the process of condensation and clumping into a gang of planets occurs. And on the right, a kind of cartoon of how planets might form out of such a planetary disk. Like me, you probably learned all those planet names in elementary school. I was told there were 9 planets, but nowadays Pluto has been demoted to an ice ball Kuiper belt object. Okay, doesn't make me like Pluto any less. But at any rate, if you were paying attention, you probably also learned that there's quite a difference between the planets of the inner solar system versus the outer solar system. The inner planets are smaller, dominantly rocky worlds, and further out are the so-called large gas giants, Jupiter, Saturn, Uranus, Neptune. And the reason for this distinction is the fact that during planet formation, the region closer to the sun lacked much in the way of solid ice chunks. That's where the dominant material was just metal and rock, the stuff of the inner planets. Further out, volatiles were in solid icy form, allowing them to grow and generate the big gas giant worlds. So, the distinction between rocky and inner planets and the more distant gas giants is really an artifact of the thermal gradient in the initial solar nebula. Hot close in, cold further out. Okay, let's get to our home world, Earth, an inner rocky world where geology takes place. In fact, geo means Earth. Of course, already geology, whether that term is truly appropriate or not, is being applied to other planets as we explore the solar system. The sun, above and shown on the chart to my right, is a typical star made up of mainly hydrogen and helium. And although in much smaller abundance, some amount of nearly all 92 naturally occurring elements. The sun formed out of gas and dust that was effectively recycled material from pre-existing stars and supernovae, largely because of the thermal gradient within the early solar nebula. The Earth's bulk composition is pretty different than the sun itself. As you can see on my left here, the Earth is dominated by metals, silicon, oxygen, magnesium, the elements we find in rocks. The Earth, well, I guess the baby Earth, if you will, undergoes a really key development at about 4.3 to 4.5 GA, meaning giga-annum, or simply billions of years. It becomes layered, what we call planetary differentiation. Earth is getting whacked by impactors, which is how planetesimals grow. And it heats up from the kinetic energy of impacts, compression, radioactive decay, and the release of gravitational energy as drops of liquid metal sink down to form a core. The surface back then? Well, a bit conjectural, but as in this image here on my right, it must have been a seething and roiling zone of magma, solidifying and then remelting. Lightning from static discharge in a hydrogen-helium atmosphere, and the newly formed moon hanging huge in the sky as it was vastly closer to us billions of years ago. We'll come back to this time period when we really consider the formation of the first few continents. The details of Earth layering have only come to light in the last century or so, and primarily from analysis of seismic waves. Earthquake-produced jiggles that go shooting through our planet. But long before seismology gave us CAT scans of Earth's interior, scientists knew that something was up. They knew that Earth's interior was probably not homogeneous. I'll spare you the mathematical details, but it's relatively simple. In fact, it just requires knowing a little bit about how much and how gravity works. Thank you, Isaac Newton. Using Newton's equation for gravitational attraction, and if you know the attractive force on an object at Earth's surface, what we call the acceleration of gravity, around 10 meters per second squared, then you can calculate Earth's mass. And ever since the ancient Greeks, folks like Eratosthenes, we've known the approximate size of Earth. And finally, if you know size and mass, you get density. It's just mass over volume. Here's the hitch though. If you just divide Earth's mass by its volume, its bulk density is around 5.5 grams per cubic centimeter, way denser than the average continent rock or ocean rock, indicating that down below there must be some really different stuff with really high density. Today, we know that Earth's core is where all that iron went, along with a few other elements, and it's indeed a place of super high density. Well, I'm worn out. We've gone from the Big Bang to stars, to planets, and to Earth's earliest history and its differentiation into layers. Plenty for now. In the next lecture, we'll tackle the origin of the moon and oceans and atmosphere and life. See ya.